Fluid dynamics deals with motions of gases and liquids, and with how these motions are related to forces. For this film, we have designed experiments in which gravity, electromagnetic, centrifugal, Coriolis, in fact all body forces, as well as viscous forces, are relatively unimportant. The centrifugal and Coriolis forces referred to here are present only in rotating reference frames. The main force, accounting for the fluid acceleration, will be due to normal stresses, to pressures. All the experiments will be in steady flow. This is the test circuit used for many of the experiments. Water from the sump is pumped to the diffuser and into this large low-speed settling chamber. The honeycomb straightens the flow, and these screens reduce the turbulence level. The flow is accelerated by this nozzle into the test section and then discharges back to the sump. Our first experiments have to do with changes of pressure and velocity in the streamwise direction. Our first test section is a contraction of cross-sectional area. This is how it fits to the nozzle. Static pressure manometers are located at the upstream and downstream cross-sections. Now let's look at the experiment. Here is the diffuser, the settling chamber, the nozzle, and the test section. My colleague Charles Kahn is inserting the static pressure manometers. And now he has started the flow. We see that the pressure falls from the upstream section to the downstream section. What about the velocity of the flow? Since water is nearly incompressible, the volume flow entering the contraction must equal the volume flow leaving, or else mass would be created or destroyed. But the volume flow is equal to the average velocity times the cross-sectional area, so the area decrease should produce a velocity increase. The velocity field is shown here in half of a symmetrical contraction by tiny hydrogen bubbles electrolyzed at a wire in the water. Each fluid patch accelerates and shows the velocity increase with distance. Because of this velocity gradient, the front edge of each patch moves faster than the rear edge, and each patch stretches out. Water is nearly incompressible, and the flow is two-dimensional, so the area of each patch cannot change, and it becomes thinner as well as longer. The velocity increase in the contraction is coupled to the pressure decrease by Newton's law of motion. Let's see how. Here, the bubbles mark many streamlines. Let's imagine that this is a typical fluid particle. For thinking physically about the problem, it is helpful to use the streamlines S and the normal trajectories N as curvilinear coordinates. First, let's look at the forces and accelerations along S for the typical fluid particle moving with speed v along S. Here is the particle enlarged. Since there are no viscous stresses, the normal stress at a point is uniform in all directions. It is a scalar, which varies from point to point. The net force on the particle acting along S comes from the difference of pressure on these two faces to the pressure gradient, dP ds. The acceleration along S is related to the convective increase of velocity as the particle moves along S, and, in Eulerian description, is equal to v dv ds. From Newton's second law, force per unit volume equals mass per unit volume times acceleration, we get Euler's equation of steady motion along the streamline. This minus sign tells us that a velocity decrease in the streamwise direction is accompanied by a pressure increase, or conversely, a velocity increase is accompanied by a pressure decrease.